here today. I'm Ben Taub. I'm Senior Vice President with Evaporcool, and joining me is Jack Wallace, also with the company. He's located here in California. Today we're going to talk about our technology and our product and hope to answer as many questions as you may have for us. So, as the name sounds, what are we doing? We are a technology that is focused on air-cooled chillers, retrofitting air-cooled chillers, or even new air-cooled chillers that pre-cools air coming into an air conditioning unit. So today I'm going to walk you through the system and talk to you how it works. A little bit just in general is that you will see, and I'll show this through documented case studies, that, and these are real examples, that we do reduce energy use on site immediately. We do have obviously a sustained energy efficiency component that does reduce peak. We reduce overall maintenance. We have the ability to improve tonnage capacity on units, reduce head pressure, system reliability, protect coils. We're going to talk all about a variety of these pieces today. So the system is comprised of relatively three parts. The first part of our system is what we call temper wrap, and the temper wrap system basically is a process that we wrap the cold suction line in an HVAC system to help pre-cool that water that's going into the actual unit in itself. The second part is sort of the brains, or the control system, which is our control box. This control box monitors temperature, humidity of outside air, and is programmed to set off the application of the spraying system onto the filters, so that as the air is coming through, or as the air is being pulled through the system, that it is getting that flash evaporation. This box in itself has a unique life that it can live as the future of our product and our technology increases, is that this system has the ability to interact with building management systems, and really so that the building management system can see real time what's happening at an HVAC unit, specifically at each unit. And then the third part is the frame in itself, and I'll show you pictures of what it looks like. But the frame attaches onto the outside of the coil area of the unit, and that frame has three parts to it. It has the nozzles where the water is being sprayed. It's got a filter media, and it's got a screen, and that's attached. And all this is being done attached through magnets. Over the last 7 years of the company's history, we've spent time working on roofs and understanding what facility managers, operators need. In the early days, we screwed these products right into units, and over time, when they had to have some maintenance done, we realized that 2 screws got put in and 4 screws got left out, and things were hanging here and there. So, as we progressed, we went to using industrial strength magnets, so that when someone needs to come in there and do some work, they can pull it right off and put it right back on. And clearly, the principle is relatively simple now, that understanding the components, as the air passes through, the outside air passing through our system, it's being flash evaporated through the control box, understanding what the temperature and humidity is. And as the air comes in, you're going to see a temperature drop from outside air to going into the unit, so the unit's not working as hard. And I'm very much simplifying a lot of the mechanics of this, but we can get into more detail. So just a couple examples to give you a sense, really where we start our installations is anything that's 20 tons and above. So most units that are 20 tons and less are not applicable, or they could be depending on the scale. It's really about scalability, but 20 tons seems to be our minimum where cost effectiveness works. This is just some examples of installations. RTU train system in Atlanta, Georgia. The one I showed you previously was in Houston, Texas. This is one here in California, in El Dorado Hills. We also can apply this to Liebert type units underneath in a horizontal application. And as well, we can do a refrigeration too. Already got a 5-minute sign there, so I'm going to speed through these. Let me talk to you about some case studies and just to give you an example of what's been going on. When we look at the real applications and the measurement verification that occurs, we look at cooling degree days, which is at anything above 65 degrees Fahrenheit, and we run our methodology based upon weather data. We typically go in and do a baseline. We've done this in the past. We now do it in partnership with utilities as they need us to. The baseline's taken, then there's a pre and post evaluation that occurs. So just to run through a couple examples, this is a 40-ton package unit in Houston. You can see that based on the cooling degree days, the amount of savings we were receiving. The bar chart shows the green bars without the Evaporcool system and the blue chart with the Evaporcool system. And you can see the percentages of savings going on, but there's nothing under 17% savings on that unit that was occurring based upon that day's use. And it goes all the way up to 31%. So these are real savings. These are not something that we've manipulated in terms of a spreadsheet. An 80-ton unit in Memphis, again, you can see the before and after, but over 15%, 18%, 19% savings. A 70-ton unit in Alabama, again, same savings, averaging around 20% savings. We'll talk a little bit about this, and I'll actually have Jack talk more about what's happening on the maintenance side of it, but there are additional maintenance savings that occur. So when we do an installation, we require that that unit have its coils cleaned. And once those coils are cleaned, we then put our system on. Our system protects the coils. It's fair to say that after our installation that many building owners don't have to have their coils cleaned again because there's a protection now that's sitting in between where there was nothing, and now there's a filter fabric and a medium that's protecting everything that's coming through it. We've been through full UL testing, and just an example, it's kind of a before and after of a system that clearly hadn't cleaned its coils in a long time. We did our installation after, and you can tell, obviously you can see the difference in the opportunity to protect those coils. Due to time, I don't think I'll talk a lot about this unless you want to add something on just condenser coil side. Okay.
I'll wait for that.
Okay. I'm sorry, I'm flipping through some slides because I want to make sure we get to your questions. And then this is another example of a data center project we did in El Dorado Hills, California. Their issue was capacity. Capacity being the issue of not being able to put another unit on the roof. And so they brought us in for a solution, and our solution was to help them increase tonnage. And through putting on the system, we were able to, in essence, calculate a 16% tonnage savings that they couldn't have found by simply they didn't have room to put another unit on the roof, so we had to have a solution for them. And the solution actually did help them lower temperature and also increase tonnage capacity. So there always is going to be a question about water, and yes, the system does require water, but there's two things to understand. One, that water is sprayed at a very minimal amount of time. It may be that the spraying goes on for 3 seconds or 2 seconds or 8 seconds, but it's not continual. It's obviously going to be based upon the temperature that's coming in. And from a consumption standpoint, this is an example of a consumption standpoint depending on water pressure, but you're roughly looking at anywhere between 6 gallons to 2.5 gallons an hour of water consumption. It's not highly consumptive, and we continue to work on the efficiency based on the water side of it as well. One thing to notice is that there is no water waste. The system only sprays what's needed. So there's no drip off, there's no runoff, there's no trough system. It is simply being put onto the pad. The pad is evaporating it off, and it's being used. We do require water treatment. That's the other thing. We can't just take standard water that's coming in from a pipe. We do have to have some type of water treatment system that will bring out the mineral content. So we have 2 systems we use. We either use a salt-based resin system or we use an ultrasonic system that's radio frequency that knocks out the minerals. And then finally, I want to conclude with one component of a question that came up earlier about utility rebates. We are working with utilities around the country. We have rebates from a variety of utilities. We're working with PG&E and have worked with PG&E for the last couple of years. We've been working on a standard calculation tool with Dave Alexander and his team as the projects are out and being closed. We have been working with Texas utilities and Tennessee utilities and Indiana utilities, and we do have a variety of utilities that have given rebates to products. PG&E has given a rebate to our product, and we've worked with SMUD as well. So with that, I got the stop sign, and let's answer questions.
I was wondering about the algorithms that you use to do that. You said there is no circulating pump, so 100% evaporation. So you're sensing. Can you explain that? You're sensing moisture, and so when there's no more cooling, you're now turning the nozzles back on. You talked. Just to, I guess, follow on to that is when you're spraying this water, you're then creating the cooling effect. You talked about gallons per ton or something. Per hour, is that a per ton measure, or is that a net on that 30-ton unit that you had on 50-ton?
It's a maximum, is what it is. It's a maximum amount of water that you could spray if you were running at full bore. Now, let me explain the operation of the system. The way it operates is there is a lockout that locks it out if the air temperature, the ambient air temperature, is below a certain degree, which is normally 60 degrees. If it's above 60 degrees and your system is running, which means your compressors are running, your condenser fans are running, then we are allowed to operate. 60-degree dry bulb, but we use total enthalpy to determine whether we operate or not. We have a humidity sensor as well as a ambient temperature sensor to determine that. We operate based on head pressure or liquid line temperature. So we have a sensor that sets on the liquid line, and we determine based on the refrigerant type what the optimum head pressure should be. And when it reaches that point, if the lockouts are made, we will start spraying at probably a 3-second interval, and we'll be off for 3 minutes. So we'll get a burst of spray for 3 seconds, and then it'll shut down for 3 minutes. If the head pressure doesn't rise, it'll maintain that level of operation, which is very, very minor. If the head pressure continues to rise and the outside air temperature continues to rise, the humidity will be going down, and we will start spraying more often. And at probably 110 degrees, ambient temperature will be at maybe 5 or 10% relative humidity, and the system will be spraying every 15 seconds for 3 seconds. So does that help you with? Okay.
So do you have consumption curves, water consumption curves for different ambient temperatures? Or?
Yes, we do. There's a lot of things that determine the amount of spray. One of them is the temper-wrap. If you chill the water first, you need less water to achieve the same goal. Sure. On refrigeration systems and split systems, we can't get to the suction line of the compressor, so we don't have that option. So it sprays more water, a little more water on those systems.
Okay.
I'm sorry, Paul. The temper wraps, just as you were talking about that, that's in the suction line?
Goes on the suction line to the compressor.
Okay, got it.
Okay, so where we're going with this discussion is that for the utilities to be able to incent this product, if we were looking at ways to help our customers put it in, the costs of the technology, the costs of water, as well as the associated energy savings for the 16 different California climate zones, obviously we would have to somehow get there to try to figure out what all of those numbers would be and the overall impact for the country.
Absolutely, you would. But remember this fact. Evaporative pre-cooling saves energy, correct? We all know that. With this particular system, it uses less water than any other system out there because every bit of water is used. Nothing goes to drain, nothing recirculates. It all evaporates on the pads in front of the coils to give you a cooling effect. So if you want evaporative pre-cooling, you can't get a better water-saving device than this one.
Okay, I believe you. We just need to have the numbers to go along with,
Yeah.
with the
And
claim.
part of the answer to your question is some of the work that's already been done with PG&E and UC Davis from the cooling center standpoint. There is this calculation tool that does take all the California climate zones into the equation.
Yeah. Both SMUD and PG&E have tested the product, and they both have used water meters to determine water consumption.
Oh, hello. Okay. Yeah, our test is about to be concluded. It's the second year of testing. The basic question that we had was in the fall or spring when there were low loads, it seemed to use more energy, more fan energy. And so that's why we went through a second year of analysis. And I don't have that data yet. I have a third party that's going to be analyzing it and reporting that to me, but that's forthcoming here shortly.
Can you explain more fan energy?
Yeah, so SMUD is testing, the issue is that you're putting this obstruction, if you will, in front of the inlet to the condenser, so you're increasing fan energy. There's a pressure. There's a pressure differential. We suspect that that's what's causing the increase in energy use, or that the numbers that SMUD perhaps found out are.
You think you're seeing higher energy use on your fans?
The data from the first year suggested that. That's why we've gone through a second year to get clear about whether or not that's happening.
Okay. Yeah, I think the answer will be revealed, and it'll be different than what you see. I believe the system wasn't running part of that time, and therefore you would have more fan operation because we had no water going on the system. Is this at UC Davis Med Center?
Yes, yes, yes.
Yes, and I think that's right. I mean, I guess the data. This is the kind of thing that we do in ET. I guess this is there are benefits during the times that we do need, relief, if you will, from the grid and so on. But there is a penalty that we need to be conscious about. It may not be a significant one. We'll find out, I guess, how significant it is. And in balance, we'll have to assess in balance what it means to the customer.
Yeah. Now, Bruce, Dave Bisbee did a test at Park Sacramento a couple of 3 years ago. And he had total water consumption there along with energy, and they produced a very large report on that one also.
Right. Well, and Dave Bisbee passed this UC Davis project over to me with the direction about what I've just said.
Okay.
Okay, I think time's up. Yeah, I'm being signaled. I'm sorry. I will take your question probably during the break. So let's move on to the next presenter. Thank you so much.
Thank you.